Okay, so to summarise, we've looked at section 1.5. We've been able to define what relative atomic mass is, the mass of an element taking each of its isotopes and their relative abundance into consideration relative to 1/12 of carbon-12, and the relative isotopic masses, the mass of one specific isotope relative to 1/12 of carbon-12. We've been able to demonstrate how to use mass spec to calculate the relative atomic mass of an element and predict which isotopes are going to be present. We have looked at how we then use mass spec to deduce the relative formula mass of a compound, okay, looking at the final M plus peak to give us the mass of the element, the mass of the compound rather. Okay, we've looked at a definition of ionization energies, the energy required to convert 1 mole of atoms in the gaseous state to 1 mole of its 1 plus ions in the gaseous state. Okay, and we've explained why those processes are endothermic, because the electrons have electrostatic attraction to the positive nucleus. Okay, we've looked at how we can use ionization energy to show the existence of subshells, because there's a dip in the ionization energies as you go from group 2 to group 3, which is because we're moving from an S subshell to a P subshell, and there's a dip from group 5 to group 6, which is because we're moving from P3, where there is no electron repulsion, to P4, where there now is electron repulsion. We've looked at recognizing the SPD configuration of an element, looking at sodium as an example, and why sodium has an electron configuration of 1s2, 2s2, 2p6, 3s1. We've looked at how we use electronic configuration to determine the chemical properties, that every element in group 1 is going to have its outer electron in an s orbital, so they have similar properties. Every element in group 2 is going to have 2 electrons in its outermost s orbital. Every element in group 3 is going to have its outer electron in a p orbital. Okay, and how that dictates their properties. Okay, we've looked at explaining what periodicity actually means, and how we can use periodicity to look at, using the successive ionization energies, how we can predict what group an element's going to be in. Okay, and we have also looked at our melting points, and how we explain the trends in ionization energy and explain our melting points. Okay, 2 final points to look at. The first one is to look at the shapes of the p and the s orbitals. So an s orbital is a sphere. Okay, and obviously the 2s orbital is going to be a bigger sphere than the 1s orbital. Okay, and the p orbitals, I have 3 of them, px, py, and pz. Okay, they are dumbbell shapes, okay, where they dissect the x-axis, the y-axis, or the z-axis. Okay, each of them has a node. So these are electron density maps. So in my s orbital, the reason why an s orbital is spherical is because the likelihood of finding your electron anywhere in that orbital is exactly the same. The reason why p orbital is dumbbell shaped is because there's a point called a node where the probability of finding that electron is 0. Okay, so I shade these to show that at one point my electrons are either in the top half of the orbital or the bottom half, but they cannot be in both because my node has a probability of 0, so the electron cannot travel through my node. Okay, and then finally we need to look at how we actually predict the use the periodic table rather to name the sections in my periodic table as S, P or D. Okay, and the way we do that is look at my periodic table, which I've very badly drawn. Okay, if my outermost electron is in an S shell, then I'm in the S block. That's going to happen in group 1s and 2. If my outermost electron is in the P shell, I'm in the P block. That's going to happen in groups 3 to 8. And if my outer electron is in the D shell, I'm in the D block, and that's going to happen in the transition metals. So, you can use these videos to play back sections that you want to revise for your section 1.5.